Hello, in this lab report, I will be discussing the properties and analysis of an object that is dropped straight downward from rest. First, the motion of the object will be recorded as a video and inputted into the program tracker. Then, the motion will be analyzed using two different computational models. The first model will show gravity as the only force acting upon the object, and the second will simulate the impact of a drag force in addition to gravity. The object that was chosen for this project was a crumpled piece of printer paper with a spherical shape, and it was dropped from rest. This is the video that displays the motion of the ball of paper. Then, the motion of the ball will be analyzed frame by frame in the program tracker. The axes that are used in tracker determine the direction in which the object is moving. For this experiment, the positive x direction points to the right, and the positive y direction points upwards. This means that as the ball of paper drops to the floor in the video, it is moving in the negative y direction. Because the ball drops in a direction that appears slightly slanted on camera, the axes have been modified so that the ball moves only in the y direction. Tracker will propagate a motion graph and table showing the position of the ball at each interval in time. For this experiment, the change in velocity in the y direction will also be analyzed, so this was included in the table and as a velocity versus time graph. As you can see, the position of the ball appears to form a half parabola over time. Newton's first law tells us that an object will remain at rest or moving straight at a constant speed unless it is being acted upon by a net force. Because it does not form a straight line, there is a net force acting upon the system. The velocity versus time graph shows that the velocity is changing at a constant rate, which means that the net force acting upon the object is constant. To describe the predicted motion, we need to address Newton's second law of motion, or the momentum principle. This principle states that the net force is equal to the derivative of momentum with respect to time. This can be written as the velocity update formula, which is pictured here. Because the velocity is changing, delta t is not equal to 0, which means that a net force is present. To simulate the motion of the ball using GlowScript, first we will use a model that includes gravity as the only unbalanced force acting on the ball of paper. Several changes to the starter code were made. The ball's measured mass, initial position from tracker, and initial velocity of 0 were inputted. Then, the program was set to run for the amount of time that was analyzed in tracker, the net force was defined as the weight force, and the equation for the weight force was also added. Lastly, the velocity update and position update formulas were edited so that the values of each variable would change incrementally throughout the program. Note that the drag force does not play a role in this model. This is the final code for the first model. This is the program as it runs. As the program ran, the ball in the model moved similarly to the motion of the ball of paper in the video. It traveled straight downward in the negative y direction, and its speed increased over time. However, as this model is compared to the actual tracker position data, it's obvious that there is a discrepancy. As the ball moves away from the x-axis, the predicted distance becomes higher than the actual distance traveled. This difference suggests that this may not be the most accurate model to predict the motion of the paper ball. For the second computational model, the force of drag will also be acting on the object. One of the constraints for this experiment was that the drag force must be proportional to the square of the speed of the object. B will be the drag coefficient that is used in the Python code. Because this force opposes the direction of motion, it will slow down the object, which will not travel as far in the same amount of time. To update the GlowScript code to include the force of drag, only a couple changes were necessary. First, the value of the drag force was defined, and the equation for net force was edited to include the effect of drag. The B value was determined using a trial and error process, matching the final position of the object in the program to the actual final position of the ball of paper. At 0.528 seconds, the ball of paper had traveled 1.15 meters. The B value was set to replicate this change in position to accurately simulate the force of drag. This is the updated program. As the ball moves downward, it accelerates less than it did in the first model. This graph shows the actual motion of the ball compared to the Model 2 position data that was generated by the GlowScript program. Even though the predicted position differs slightly while the ball is in motion, the curve of the graph stays very consistent throughout the entire time period. This graph shows the position data and trend lines of both models and the actual data from tracker. The inclusion of the drag force causes the ball to accelerate less in the negative y direction, so the final position vector has a lower magnitude in the second model. You can see that the model that includes both gravity and drag is much more accurate. As Model 1 diverges greatly from the actual motion, Model 2 remains similar to the actual position. A terminal velocity is reached when the velocity stops increasing and there is no net force acting upon the object. This occurs because the drag force and gravity are the same magnitude, so the object continues falling at a constant velocity. This graph shows the velocity of each model with respect to time. The terminal velocity would be reached as the slope of the velocity approaches zero. However, the two models and actual velocity are still changing, so none have reached terminal velocity at this point in time. However, it is apparent that Model 2 is closer to reaching terminal velocity than the other two data series. Imagine that the ball of paper is thrown straight downward instead of being dropped. Will it reach a terminal velocity faster? To answer this question, the computational model was changed 3 times to simulate different initial velocities. Even when the object was thrown with a downward velocity, it reached terminal velocity at the same time. Because of this, it can be observed that an object will take the same amount of time to reach terminal velocity regardless of its starting velocity.